You've seen them before, right? Medical scans, X-rays, MRIs, CT scans. And it's easy to think, okay, that's just a high-tech photograph of my insides. But what if I told you that's not even half the story? That these images are so much more than just pictures? Well, today we're going to dive in and uncover the incredibly rich world of data that's hidden inside every single one.
So take a look at this. What we're seeing is a procedure happening in real time, an endoscope being guided inside a patient. It looks like a live video feed, doesn't it? Super clear, immediate. But here's the thing. What we're actually seeing is the final product of a really complex data journey. It's a visual translation of energy that is completely invisible to our own eyes.
And that really gets to the heart of what we're talking about. What is that underlying data really telling us? How does a machine turn something totally invisible into an image that can literally save a life? Well, let's find out.
To really get it, we first need to appreciate the massive leap from old-school analog film to the digital world. And trust me, this wasn't just some minor upgrade. It was a revolution that completely changed what was possible in medicine.
This slide really breaks it down. With analog film, there's a direct physical link. Radiation hits the film, silver granules get developed, and bam, you have a dark spot. It's a one-to-one thing. But digital, it's a completely different universe. It separates the data from the display. The image you see on the screen is just one interpretation of a massive pile of numbers, a perfect grid of pixels you can copy and send across the world with zero loss of quality. And that is the key advantage. A digital image is pure data, which means it's incredibly flexible and ready for all kinds of electronic manipulation.
So how is this data captured in the first place? Well, pretty much all medical imaging is based on making the invisible visible. It's about measuring forms of energy that our eyes could never ever detect on their own.
Different machines are basically experts at seeing different kinds of energy. X-rays measure how photons pass through you. MRI, on the other hand, listens for faint radio signals coming from hydrogen atoms in your body's water and fat. Then you have PET and SPECT, which are amazing. They actually detect gamma rays coming from a radioactive tracer inside of you. And of course, ultrasound just listens for the echoes of sound waves. Each method is capturing a totally unique physical property of your body.
And regardless of the energy source, the fundamental challenge is always the same. You have to take a continuous, real-world signal, like the varying strength of an X-ray beam, and convert it into a discrete digital grid of numbers that a computer can actually understand and store. This whole process is called discrete sampling.
All right, so let's see how this grid of data actually builds into what we recognize as an image. You can kind of think of this grid as the image's digital DNA. It's the fundamental code that holds every single piece of information.
The fundamental particle of this digital world is the pixel. We've all heard the word, right? But each one is just a single tile in a giant mosaic. And each tile isn't just a color, it's a number. A number that represents the average signal intensity, the average X-ray strength, or the average MRI signal from one tiny, specific spot in the body.
And this image illustrates that perfectly. When you see a high-resolution MRI like this, it looks smooth and continuous. But it's actually made up of millions of these individual data points, these pixels, all arranged in a perfect grid, just like that low-resolution overlay is showing us.
So if each pixel is a tile, how much information can each tile hold? That's determined by something called bit depth. The easiest way to think about it is this. Think of bit depth as the number of crayons the computer has to color in each tile. The more crayons it has, the more subtle the shades it can represent.
And this is the part that just blows my mind. A standard photo might be 8-bit, which gives you 256 shades of gray. But a typical medical image, it's 12-bit. That gives it over 4,000 shades of gray. Now here's the kicker. At any given moment, our human eyes can only distinguish about 30 of those shades. The image data contains vastly, vastly more information than we can possibly see all at once.
So if all that information is just hiding there in the data, how do doctors actually see it? Well, this is where the true power of digital imaging really comes into play. We can use software to explore that huge range of hidden data.
This is done using a technique called window and level. So imagine all those 4,096 shades of gray laid out on a long ruler. The window is like a magnifying glass that selects just a small slice of that ruler, say the shades from 1,000 to 1,200. The level is what you use to slide that magnifying glass up and down the ruler. And then the computer takes just that narrow slice and stretches it out to fill the entire display, from pure black to pure white. That makes tiny differences in that one specific range incredibly obvious.
Let's see it in action.
Here's an X-ray of an elbow after surgery. With this particular window and level setting, we're looking at the slice of data that corresponds to bone. The bone structure is beautifully clear, and a doctor can assess how it's healing.
Now watch this. This is the exact same data file. We haven't taken another X-ray. All the radiologist did was slide that window up to a different range of values, the range that corresponds to metal. And suddenly, the bone detail vanishes and the metal screws and plate just pop into perfect, sharp focus. This is the magic. One scan contains multiple images, all just waiting to be revealed.
As medical physicist William Hendy wrote, this is really the core of it. Digital imaging isn't just about taking a picture, it's about acquiring a rich data set that allows for incredible post-processing, letting us enhance exactly what we need to see.
But not all images are created equal. Just having the data isn't enough. For an image to be diagnostically useful, two key factors have to be in balance: resolution and noise.
Think of it this way. Spatial resolution is just clarity, the ability to see two tiny separate things as two tiny separate things. More resolution means more detail. Noise, on the other hand, is like static on the radio. It's random variation in the signal that isn't part of the true picture. If you have too much noise, it can completely hide what you're trying to see.
And this is what noise looks like. This grainy pattern is called quantum model. It comes from the simple statistical reality that photons don't arrive at the detector in a perfectly even stream. When we enhance the contrast to see subtle details, like in image B, we also end up enhancing this underlying noise, making it much more visible. So, the ultimate goal, the measure of a truly great diagnostic image, isn't just about having high contrast or low noise by themselves. It's about achieving a high contrast to noise ratio, or CNAR. This just means the signal from the tissue you care about is much, much stronger than the random background noise. That's what allows a doctor to make a confident diagnosis.
We've seen that a medical image is this deep well of data, far richer than what our eyes can perceive. Doctors use tools like window and level to manually explore it. But this leaves us with a pretty fascinating final question. As artificial intelligence and machine learning get more powerful, what new patterns, what hidden secrets will they be able to see in this data that we've been missing all along? The next chapter in this story is really just beginning.